So hello. Today I wanted to do this video to quickly introduce the notion of state machines or algorithmic state machines, like the SM charts, which are on the lab, and together with what I've provided in the previous video, we should be having all what we need in order to tackle our lab. So let's go to the point. So what are ASM, or what are state charts? Uh, so I'll move straight. I'll be skipping some of the slides here, but the slide I'm showing here are from the lecture book or from the textbook Fundamental of Logic Design, is the Unit 19. You don't have to read everything in detail. Just if you don't understand, you can, or when we're done here, you can go back and then read the book again. So, what are state machine charts? So, state machine charts are a way for us to construct a charts that will allow us to, in general, generate a code, not for the hardware implementation, but this code is usually intended to be running on a software processor, like a microcontroller. So remember, in the past, we used to have embedded system implemented, and today we still have that implemented in microcontroller, and then we like to implement finite state machine. Those finite state machine, we could do them in hardware the way I did on the video that I provided online and the way we did in the class. This is the classic way of doing finite state machine in the hardware, and this is the way that I like you to learn. However, because the algorithmic state machine, as the name indicates, algorithmic, has also been there for very long time, very old, mostly for the implementation of those finite state machine, but in software, we felt the need to include that here. So I still see that out there, but this is not really the normal way of doing finite state machine. So what is an ASM? An ASM is a chart that consists of a certain number of blocks or certain number of components. We have the state. The state is usually represented as a box like this with one entry point and one output point. This entry point will have the name of the state, and sometimes we will also have the output while we're in that state. Where is that important to give an output when we're in a given state? If we have a counter, for instance, that counter, you can just attach the output to the state, right? If we're in state 5, then 5, we output 5 here, or that 5 goes to the decoder for the 5, and so on. So we can output the state, the value in the state themselves, as opposed to outputting the value on the edge on the transition from one state to the next one, like we've done with the Mealy automat. When we output the value in the state, usually this is done in the Moore type automat that we're going to be discussing on Monday. Anyway, we have our state representation here, and this state representation, again, we have the name, and then we have the list of output, everything that we're going to be outputting in this state. For now, it's not that important. And then you have a code that could be executed also while we're in this state here. This reminds us somehow of something we call finite state machine with data part, a type of finite state machine that allows us to perform also complex operation there. But in general, finite state machine are just to control the behavior, moving from one point to next one, checking that condition are fulfilled, storing the value until we get the behavior that we like to have. So we have this state box. If your finite state machine has 20 state, then you likely may also have 20 of those boxes. Then we now have what we call the condition box. The condition box has one entry point and two output points. One entry point is how we get into that condition box. That could be coming from a given state or from another condition box. So we're moving from one state to a condition box or to another condition box. And that condition box has a condition inside. So it's in a diamond form, has a condition inside. And if the condition is true, we'll be going to one side of the branch. In this case here, the left side. And if the condition is false, then we'll be going to the right side, right? And the last type are the conditional output list. This conditional output list is when you're doing a transition from maybe one state to the next one, you could be having a condition after that. And then if one of the two conditions are fulfilled, you could output something. And this is usually the behavior of the transition from one state to the next one, as we've learned with the mealy. When you transition because a condition is causing this transition, that condition is true, then you also output a value. That output of this value is going to be on this node here. So we have three type of node, and this is what we need to use in order to build all kind of finite state machine that we would like to have. Why are we bothering you with that? For you to know that this exists. But in general, this has been meant to generate software codes that run on things like microprocessor and then perform the same type of controller that we have on the hardware. So how do we build finite state? How do we build this type of algorithmic state machine? In literature, we're told that we build that from an SM block. And this SM block is usually a block with one entry path here and then multiple output path. That's a definition that we're providing here. And then from here, we can build our algorithmic state machine. Still not very interesting for us. I'll be skipping and going toward the end because that here question is always, and where do I get this SM block, right? The question will be coming from there and so on. So for now, this part also is not very relevant for what we're going to be doing in the cloud. Now, the block now with the chart with the block here is very important for us. Why do we need the block with feedback here? We need a block with feedback because sometimes we're going back to a given state or when a condition has been fulfilled and we need to get back to the same state. If we're looping in the same state, we need to have this feedback loop, right? How do we implement the feedback loop? You have a condition, that condition could be true or false, and depending on the condition, we ask you to return. You cannot do a return on the same condition, otherwise you'll just be doing an infinite loop here. The condition, we do a return. In general, we do the return not on the same point here, but we do the return at a given state. Because we have the return at a given state, that will allow us at least to have this state here being somehow stable, getting a value in there before we can move forward. And therefore, something like this here is not correct when you're building your ASM chart. You always have to return at the level of the state here because that's where we're going to be evaluating everything when we get into that state. So what else? Okay. Sometimes we have description that is given to us in parallel. Like in this case, you have this block here where we have the state S0 and then the output Z1 in that state. And then from here, you can evaluate the X1, you can evaluate the X2, you can evaluate the X3. This here is a description in parallel. When we do that in hardware, we do all this here at the same time. And then when we evaluate this condition and it's true, we will output the Z2 and get out here. If the X2 is 3 is correct, then we'll output the Z3 here. And then if X3 is correct, then we'll output the Z4. So this type of behavior, we don't have it in software. So therefore, you can implement this exactly like this here in software. And the algorithmic state machine allows us to implement this type of behavior that appears parallel to emulate that sequentially in software. So how do we do that in software? We'll just do sequentially. We'll do the first branch here. Then when we're done with this here, we jump into the next branch, we do it. And then when we're done with that, we move into the next branch here, and then we do it. And the result of that is given here. So we're starting with the S0, Z1. That's our initial state here where we enter in this block. And then here we evaluate the X1, and then if it's correct, we output the Z2, and then we go to the branch that we will join here to move to the X2. So here we evaluate in this area. If X1 is true, we output the Z2, and then we get out. If it's not true, we just get out. And then here we're not just getting out of this block, but we have to evaluate now the X2. So we're now jumping back and evaluating this x2. That's what we're doing here. We evaluate the x2. If x2 is correct, then we output the z3. If not, we branch with the case where it's not correct. And then we down here, we also evaluate x3 and so on. And this is all what we need to know for the algorithmic state machine. When you have a condition or multiple conditions that can branch in different directions, you evaluate the first one and then you link to the second condition. You evaluate that, you link to the third condition, and you do all sequentially. The consequence of this is that those graphs here, they tend to become very large, right? So for the purpose of this class, we've learned the Mealy machine. We've not yet done the Moore machine, but just understand that the Moore machine have the output in the state. Like here we have the S0, and then where we in this state here will output the ZA. If you in state S1 would output the ZB, if you in state S3 would output the ZC. If you take a case of a counter can easily be implemented like a Moore machine. If you in state, let's say the counter here is a sequence, let's say 0, 1, and 2, then if you're in this state, we just output the 0. If you're in that state, we output a 1, and if you're in this state, we output a 2. And then moving from one state to next one is done on the condition of the clock, on the positive edge of the clock. But we've seen the Mealy. So the Mealy allows us to move from one state to transition, for instance, from state S0 to state S1 with the condition 1. If that condition is true, we'll output the 0 here and then move to this state. And now, don't worry about the Z here. For now, let's assume that we don't even look at that, or we just put that in the state. Now, this finite state automata, we know the structure of that. We've learned in class how we put the structure of this finite state automata. And the only thing we need to do now is to build that transition graph. To build the transition graph, we will take the S0 and A will be one state, S1 and ZB would be another state, and then S2 and ZC would be another state. We will start in this state here and evaluate the condition here at the input. Let's say the condition X, calling it X here, and then if this value X here is 0, then we will stay in the same state, and if that X has the value of 1, then we'll move into state S1, and then do the same in this state S1 and then in state S3, S2. So the ASM for that looks like this, starting in state S0 with output ZA, that's the state S0 and output ZA. In the case of a Mealy, where we don't have the output on this state here, we just leave it like that. Like if we didn't have the ZA here, only S0, then we'll just put the S0 here. And now we're getting into this state here without any condition. And then the code execution, you could put the code encoding of this state here like 0, 0, 0, 1, and here 1, 1. But you don't have to do that, yeah? So just leave it like that. Now, we have in this state here, the next thing is to evaluate the condition to move to the next state. Let's call the input here X, and then we're evaluating that X. If it's 0, if we have a value of 0, then we'll remain in the same state. You remember that we had a feedback loop. We'll branch back into this state here if the condition is 0. If the condition is 1, then we'll move into the next state, which was the S1 here, and then output is the ZB. For the Mealy, at this point, we don't worry about the output in the state. We just write here the S1. And then we're in this second state here, right here. And here we can now also evaluate the condition of the input. So the input here can have the value of 1, in which case we'll move to the state S2. Or it will have the value of 0, and then we'll move back to the state S0. So if you're in this state here, we branch now to this conditional state. And in this conditional state, what do we do? If we have a 1, if we have a 1, we'll move into the next state here, which is S2. And if it's 0, we'll branch back to the state S0. And then in the state S2 here, we'll also evaluate the condition X here. If that condition is 0, we'll output the Z1 here and then go back to the condition, to the state S0. And if it's 1, then we'll be branching back into this state here, but we'll output the Z2. Now, question that you'll ask to me is like, but we were in this state here, where is the output 0 here? Where's the output 0 there? So everywhere where we had the output 0, we didn't put the value 0. We didn't write that 0 explicitly at the output. It might be that the book here may be considering a 0 as a empty output. But to make this automat correct, we normally have to add the output 0 here. We have to add the output 0 here. We have to add the output 0 here. And then we also have to output, so the conditional output 0 there. Here we have to add the conditional output 0 before we move into this state. And this is all what we need to do. So for your lab 5, it's your responsibility to devise this finite state machine or finite state automata. We've seen how to do that. You need to know the input that we provided to you. You need to know the output that we provided. And then you have the state that we also provided. And then you have now to define the logic to move from one state to the next one and so on. And then you have your finite state automata. From there, you can generate the ASM. When you do the ASM, you find, just take the remaining part here, do the state and the input encoding, define the next state and the output as function of the current state and the input. We know how to do that. We've done that so many times. And then you define the circuit for it, and then you can simulate that circuit. Okay. So on Monday, we're going to be discussing how to do the whole thing in VHDL. And then we'll also go over the simulation in VHDL using test benches. Okay. So with that, you have, I believe, all what you need now in order to complete your lab for next week. Thank you very much. If you have any question, feel free to contact me. Bye. So.